welcome you to the demonstration system Process Diagnostics with SIMATIC. Nowadays it is decisive for system and machine constructors in modern production engineering to keep engineering costs as low as possible. For the operators of these systems, it is essential to keep system standstill times down to a minimum. Taking a typical problem, we will be showing you the basic principles and the product and the tools for process diagnostics. In the course of this presentation, we will demonstrate how process diagnostics, based on a fictitious fault, functions with SIMATIC components. Once we have gone through the details of the types of monitoring and Proagent, we will be showing you real configuration sequences for the following languages: ladder, function block diagram or statement list with S7-PDIAG, S7 graph and S7 high graph. Before moving on to the actual topic, we would like to give you a brief introduction to handling this demonstration system. If you don't do anything, the complete demonstration system runs through fully automatically. But of course, you also have the option of jumping directly to specific sections using the navigation page just displayed. In each shot, you can navigate just as with a standard CD player. You have options to play, stop, fast forward and back, jump to next or previous section, and also return to the navigation page by pressing the Home button. If you have any problems operating the system or understanding special technical terms, you can access Help and a glossary of terms at any time. On the navigation page, you also have the option of sending us an email via the Contact Us button, or leaving the demonstration system via the Exit button. At this point, let us have a look at the sample problem on which this demonstration system is based. Today there is strong competition in modern production engineering, which is expressed above all in increased costs and time pressure in all phases, from assembling the automation solution to maintaining the production systems. For systems and machine constructors, it is decisive to be able to guarantee high availability for their products. Let us take a fictitious fault in the system. A standard alarm system informs the operator of a symptomatic fault by a display on the HMI device. Now, to determine the cause of the fault, for example, which missing step enabling conditions are holding up the process, you need a programming specialist who has to analyze the user software with a programming device. This sort of procedure usually results in long standstill times. This is where process diagnostics comes in. It is built into the user software, and it not only rapidly informs you of a fault, but also locates it automatically, and thus helps in troubleshooting. The time-intensive employment of a specialist is no longer necessary, because all the information is displayed to the operator on the HMI device. And the operator doesn't need to have any programming know-how, nor use any programming devices. In the sections that now follow, we will be demonstrating how SIMATIC fulfills these requirements. You can define diagnostics as being the determination of a faulty function through monitoring and evaluation of the characteristic values of a system. If the evaluation of these characteristic values throws up a critical value, the cause and location of the abnormal state is determined and displayed. In the course of the process, the significant symptoms captured by the monitoring system are analyzed and the cause responsible is determined. Considering that in practice there is a lot of ambiguity between the cause and effect, the diagnostics process can be a very complex one, which is why it is necessary to have extensive know-how and experience in processes and possible faults. Technical diagnostics is integrated in an overall maintenance strategy whose primary task is to ensure high availability, especially in production systems. In the corrective case, in other words when a unit fails, the system must rapidly display the fault, locate its cause as precisely as possible, and support the operator in clearing the fault. The savings potential is highest here because standstill times in the production process can be reduced. The preventive case is based mainly on a time model. Here, using logistics tools based on time intervals, operating hour meters, etc., a warning is purposely triggered and servicing carried out reliably. The consequence here is that you might waste the service life of the unit replaced, because it might well have continued functioning a lot longer. The predictive case is based on a status model. This means that optimally the operator receives a clear and explanatory warning in good time that a fault might occur in a unit or system in the near future, or an indication is given of the remaining expected service life of the equipment. This means that practically all additional costs are eliminated. This case requires extensive knowledge of the process, because to ensure a meaningful prediction, often very many statuses and characteristic values have to be evaluated. In this respect, automatic diagnostics systems based on know-how and status are just beginning to find universal employment in the production industry. The tasks of system and, above all, process diagnostics with SIMATIC, which is the topic of this demonstration system, are for corrective cases. The diagnosis of a fault is normally based on which components of a system or machine are diagnosed. We therefore differentiate between two types of diagnostics: system diagnostics and process diagnostics. System diagnostics covers the monitoring functions that concern the correct functioning of the components in the automation system, which includes everything from S7 CPUs and function modules to network components and intelligent sensor interfaces. If a fault occurs, this could be a programming fault, module failure, access failure, etc. Then this is stored by the CPU in an internal diagnostics buffer. The service staff can run a fast and targeted fault diagnosis via PG functions. Also, the display of system faults on HMI devices requires only a small amount of configuring. In the case of a system fault, the operating system of the CPU interrupts the normal run of the program and automatically calls the appropriate fault OB. The programmer can now selectively react to each system fault individually. Process diagnostics now captures all the events, processes and components going beyond the controller in a system process. These can be defective sensors or actuators, hindered movements, or unfulfilled blocking tasks, for example. Process diagnostics cannot be automated in the same way as system diagnostics. It is system-specific and therefore cannot be built into the hardware or software like the system diagnostics. Process fault recognition requires a different monitoring strategy for each machine or system, and can only be implemented by the manufacturer of the system. The engineering tools support the programmer here by generating an individually monitoring program that is incorporated in the program processing. Integration of process diagnostics into HMI devices requires only a minimal amount of configuring thanks to ready-made standard masks. Let us summarize this. Due to the high hardware availability of today's automation components, the emphasis of the diagnostics must very clearly be put on process faults. The sense and purpose of process diagnostics is to quickly and reliably display the fault and its causes. We will now have a specific look at the SIMATIC products and tools that make process fault diagnostics possible. Process diagnostics in SIMATIC includes different additional products that are integrated by TIA into the individual overall solution via optimum system interfaces. These then provide a consistent interaction between the SIMATIC languages, the options packages, and the HMI configuration tools. Process diagnostics in S7-300, S7-400 or WinAC systems is embedded in the three languages, S7 High Graph, S7 Graph, and ladder, function block diagram or statement list. The SIMATIC languages S7 Graph and S7 High Graph support process diagnostics anyway. In other words, they provide the option of programming the relevant monitoring conditions directly next to the program logic in the sequencer and status graphs. If the user program is written in ladder, function block diagram, or statement list, then the S7-PDIAG option package has to be integrated into the Step 7 development environment. Using this, you configure the signals to be monitored, plus the monitoring regulations and the associated message texts. On top of this, S7-PDIAG automatically generates the required monitoring blocks, which contain the complete monitoring logic and mechanisms for transfer to the HMI devices. In the languages listed, the configuration is stored via a system-wide interface in one common database on the configuration computer. This circumstance permits single-step configuration of the process diagnostics. In other words, all the configuration tools involved automatically access the database and take the relevant data or store the data required for other packages there. The visualization tools for ProTool or ProTool Pro and WinCC are enabled in each case by the Proagent option package for seamless integration of the process diagnostics into the HMI system. This contains ready-made and pre-connected standard pictures which, with a minimum of configuration, integrate the complete function sequence for process diagnostics into the HMI device concerned. Process diagnostics can run on the following HMI panels: OP or TP27 and 37, OP or TP270, compact device C7626, MP270 and MP370, on each PC with ProTool Pro and WinCC, with WinCC, for example, on the SIMATIC panel PC FI45. Now, by way of example, we want to follow a process fault during runtime through the schematic automation system from address monitoring in the ladder, function block diagram or statement list user program via S7-PDIAG to display on the HMI device by Proagent. On the CPU side, our model consists of the user program level and the operating system functions. An HMI device with Proagent is connected via the relevant hardware controllers and bus systems. Let us presume that the various process states are read into the automation system via appropriate sensors. In one particular program logic, these signals are linked in one central release signal. Address monitoring for this release signal has been configured with S7-PDIAG. As mentioned before, the S7-PDIAG option package generates the functions and instance data blocks for this configured address monitoring. The first function block has the task of monitoring the address in its setpoint state. The second function block stores at the time of fault the state of all the signals that make up the result of logic operation of the address being monitored. The fault recognition FB monitors the addresses in the cyclic program in the user block for which the monitoring has been configured. Let us now assume that one of the sensor signals takes on a fault status. As soon as the result of logic operation shows a deviation from the setpoint state, the fault recognition mechanism stores all the signals belonging to the operation in an initial value acquisition. This information and the stored network structure are important for later criteria analysis. Then the fault recognition FB enters the fault information via an internal call of the alarm S blocks into the central message acknowledgement memory in the operating system of the S7 CPU. If the S7 communication system recognizes a change in the message acknowledgement memory, it generates messages to those target devices that have logged onto the CPU concerned. This is defined when the HMI stations are configured. The message contains, among other things, the message number, the message status, and the exact time of the message occurring. The message reaches its target HMI device via the relevant bus system and interface. Via the S7 communication system of the target device and the diagnostics handler, the final process fault message is made from the message data and the database with the corresponding message texts in the target device, and displayed in standard Proagent message pictures. The message process for this case is then completed. Here we have shown you a run for the ladder, function block diagram or statement list language using S7-PDIAG. But the principle is identical with S7 graph and S7 high graph. It is just that the monitoring process here is already an integral part of the language. This means that you do not need any explicit monitoring blocks here. Let us now turn to the analyzing process that makes it possible to determine the causes of a fault. We know that a fault has occurred in the process. However, what is important for fast troubleshooting is to locate the cause of the fault as precisely as possible. Let us go back. The monitoring block has recognized that the central release signal has left its set point state and has sent a message accordingly to the HMI device. But exactly which process signal is responsible can only be found out through criteria analysis. If the operator on the HMI device requests a detailed view of the fault, the HMI device generates a message and sends it to the communication system of the CPU causing the fault, with a request for the initial values. Now, from the relevant instance DB, the communication system of the target CPU takes the initial values of the status information, which the addresses of the networks involved have at the time of the fault, and the structure of the monitored network that is stored there. In this way, the system can then completely capture the addresses of auxiliary networks in which an interim result has been stored, a flag for example. This holds also for the case that these networks are in other blocks. A message with this content is then sent back to the requesting HMI device, and on the corresponding mask is displayed as a signal list, ladder diagram, or statement list detail network with indication of the faulty signals. From this, the operator can now determine which signals caused this fault state without having to use a programming device. In the following, we will be showing specific details for all languages that support process diagnostics, and then the integration of Proagent into the HMI device. The S7-PDIAG option package extends the scope of functions of Step 7 with the option of process diagnostics for the ladder, function block diagram or statement list language. Here there are different types of monitoring available. Using address monitoring, you can monitor specific addresses in the program or directly from the symbol list on a set point level or change of edge. The task of the configurator is to attach the error definition to an assignment in the desired network and to parameterize the predefined monitoring logic in a dialog. You have a choice here of edge or level monitoring combined in each case with a delay time. You can add parameters and any associated values to the message text that is supposed to be displayed in case of fault. Now, if the monitored address deviates from its setpoint state, the message is displayed. In addition, through criteria analysis, you can trace the address that caused the fault beyond network and block boundaries. For general monitoring, you can monitor any signals via a freely definable monitoring logic. In other words, this logic is not part of the user program, unlike the previous case. Only if the logic of the individual operation is fulfilled will the fault message be triggered. You can design an individual monitoring logic and formulate it with S7-PDIAG specific language elements in the parameterization dialog along with the message text. For address and general monitoring, you do not need to modify your user program for the monitoring logic. With motion monitoring, you check whether physical movements in your process are being executed correctly and within the specified time. S7-PDIAG offers 4 different forms of motion monitoring. Startup monitoring determines whether a movement actually leaves its start position within a predefined startup time. Action monitoring determines whether a movement reaches its target final position within a predefined time. Reaction monitoring determines whether the target final position reached is being held stable. Interlock monitoring determines whether valid interlock conditions are fulfilled in each direction of motion. Specific programming regulations have to be observed for the concept of movement monitoring. With S7-PDIAG functions, a block is supplied with standardized monitoring networks, and it has to be linked via parameters with the application-specific addresses. It already contains the necessary initial diagnostic addresses and data structures on which the configuration masks of the different movement monitoring types are set. All you have to do is assign the parameters to the marked initial diagnostic addresses using the configuration dialog provided. The monitoring logic is then generated by the system automatically for the motion monitoring concerned in each case. The standardized data structures make it possible to incorporate ready-made HMI masks, such as the manual operation mask, without having to do any programming. This option for generating standardized multiple-use monitoring blocks, which also adapt their instance-specific message text automatically, is a great potential for streamlining in engineering. With the S7 graph language, the option for process diagnostics is already an integral part of the engineering tool. The possible fault definitions are integrated directly into the sequencer with the S7 graph editor and evaluated permanently by the sequence controller at runtime. S7 graph knows 2 types of error monitoring, the interlock and the supervision. The interlock is a programmable condition which affects the running of individual actions of the sequence. If the interlock condition is not fulfilled, in other words, there is an error, an interlock fault is announced, and all actions linked to the interlock are blocked. Supervision permits you to monitor the step-enabling condition in the next step. If the supervision condition is fulfilled, for example through a time monitoring step, a supervision fault is announced, and depending on the settings, the sequencer is blocked. The error texts in both types are generated automatically with specification of the faulty step. S7 High Graph 2 has the option for process diagnostics already integrated. All fault definitions are displayed here in the editor on specially marked fault states. S7 High Graph basically distinguishes time monitoring and state monitoring. Time monitoring indicates whether a transition switches after a fixed time. If after the parameterized monitoring time there is to be branching into a fault state, then this is done via a transition with the predefined signal ST expired. With global monitoring, regardless of the actual active state, a signal is monitored constantly or globally for its state. In the program, this means that any transition with conditions leads to the error state. State-dependent monitoring is when a signal is to be monitored only when it is in a particular state. In the program, the conditional transition then comes from the monitored state and leads into the fault state. In all three types, the error text is generated automatically from the state number, the name of the graph group, and the state graph. The Proagent option package displays information on process diagnostics in uniform, standardized pictures on the appropriate display devices. They are already linked with each other via a predefined set of buttons. The message picture displays all the process diagnostics messages in the order of their occurrence. The overview displays all the diagnostics units with any subunits they may have. In the detail view, you get a display of the faulty network or the transition concerned. The display is derived from the result of the criteria analysis by marking the addresses classed as being faulty in statement list code or as ladder network. Via the motion pictures, you can visualize the state of a motion. Via direct buttons on the display device, you can go through each configured motion manually, for example after clearing a fault to get the system back to a defined state. If there is an S7 graph sequencer behind a faulty unit, then here you get a display of the steps there are and at which step the sequencer is at the moment. The sequencer can be initialized from here, or you can enable or disable a specific step. In the following, we want to demonstrate a few typical configuration sequences for process diagnostics. We have chosen a brief example for each language. In ladder, function block diagram, or statement list, we will see address monitoring using S7-PDIAG add-on. In S7 Graph, we will configure a supervision and an interlock for a step. And in S7 High Graph, we will configure a monitoring time in a state. All the examples will be visualized with ProTool Pro and Proagent. Let us begin with the example of address monitoring with S7-PDIAG. We open FB20 in the block view of the Step 7 project. This contains a general run release signal that is linked via an individual logic distributed over several networks. In Network 4, we select the assignment Gen Release and activate the process monitoring dialog. Via the New button, we want to configure an address monitoring. In the next dialog, we parameterize the monitoring of a falling edge, enter a delay time of 1 second, and the message text. The formal parameters in the message mean that when there is a fault, the faulty unit and all the signals concerned are displayed in clear text. We acknowledge the dialogues and save the FB20. Then the monitored address will be marked in yellow. We close the block editor. In the block overview, we now see that the FB20 is marked as supporting diagnostics. Since the instance DB of the FB20, in our case DB20, also needs this attribute, we open this block in the statement list editor. In the Properties dialog, we go to the Attributes tab and give the S7-PDIAG property the value True. In the block overview, we see now that after saving the block, the DB20 has also been marked as supporting diagnostics. We now call the Process Diagnostics application S7-PDIAG. In the Explorer view in the left window, we see all the units of the program that support diagnostics. In the right window, you have a display of all the signals monitored and also the type of monitoring. Via the menu item Process Diagnostics, Compile Completely, we now generate all the monitoring blocks. In the block overview of the SIMATIC Manager, we see the newly generated monitoring blocks and the required system functions. Then we open the OB1 and insert the code lines for calling the monitoring blocks. We save OB1 and close the block editor. Now we load the Step 7 project into the CPU. We open the ProTool Pro project from the project view of the SIMATIC Manager. In order to be able to configure with Proagent, we go to the menu item System and open the dialog Proagent. In the Standard group, we select the unit that supports diagnostics and transfer it to the Selected Units window. We close the dialog with OK, save the project, activate generation, and then start the runtime. As soon as a process fault is triggered for which monitoring has been configured, a pop-up window opens containing the configured message text. We acknowledge the message and switch to the message picture and to the detail view, where we can determine not only the addresses that caused the fault, but also the associated controller, the unit, and the network in which the fault occurred. With the F8 button, we can have the signals in the statement list network displayed. With F7, we get not just the links which include the faulty addresses, but the complete network. Again, with F8, we switch to the ladder view. Here too we can have both a section or the entire network shown. The following example deals with the configuration of interlock monitoring and supervision monitoring in the S7 graph language. We open the block that contains the sequencer. A supervision means that a message is triggered when the step concerned is not completed within a certain time. Depending on the global settings, the active step is then closed. We select Step 4 and insert in the wildcard for a supervision a comparator as time monitor parameterized with a monitoring time of 5 seconds. Step 4 is now marked with a V. An interlock means that a message is triggered when the interlock conditions are no longer fulfilled, and all output actions linked with the interlock are blocked. To build an interlock into Step 5, we select the step and in the relevant wildcard we insert an AND operation which we assign to the safety guard closed address. Step 5 is marked with a C. We now link the interlock to the action drill lift. If the safety guard is opened while Step 5 is active, the command output is blocked. Now we have to make the following general settings for S7 graph. We open the block settings dialog and in the Messages tab we activate display acknowledgement on the HMI device, both for interlock and for supervision. We acknowledge the dialog and then save the sequencer. Load it into the CPU and close the editor. Now we open the ProTool application. In order to be able to configure with Proagent, we go to the menu item System and open the dialog Proagent. In the Standard group, we select the unit that supports Diagnostics and transfer it to the Selected Units window. We close the dialog with OK, save the project, activate generation, and then start the runtime. Once a process fault has been triggered for which the supervision has been configured, in other words, the lower step was not completed within the time limit set, the supervision fault is announced in a message window. We acknowledge the message and switch to the overview in which we can see at which level and in which unit the fault has occurred. In the detail picture, you also get a display of the step, the transition, and the faulty address. Now, with the F8 button, we switch over to be able to see with which operation this address is linked. Another click on F8 shows us the address in the ladder view. With Shift F5, we switch to the sequencer view in which the number of the blocked step is marked red. After clearing the fault, we have to acknowledge the supervision fault. Only then is processing of the sequencer continued. If the safety guard is open during the lifting state, the interlock fault is announced. We acknowledge the fault and open the overview in which we can determine at which level and in which unit the fault has occurred. In the detail picture, we see the step concerned and the transition as well as the address that caused the fault. With the F8 button, we switch to the statement list and ladder views to see how the address is linked in the program. In the sequencer view, just as with the supervision fault, the number of the faulty step is marked in red. Once the fault has been cleared, the sequencer starts to process again automatically, unlike with the supervision fault. The following example shows the configuration of simple state monitoring in the S7 high graph language. In the SIMATIC Manager, we open the relevant state graph entitled Clamping Device. Here we want to time monitor state 2. For this, we only have to parameterize a maximum state dwell time with a monitoring time. We save and compile the state graph and load it into the CPU. Now we start the Pro Tool application. In order to be able to configure with Proagent, we go to the menu item System and open the dialog Proagent. In the Standard group, we select the unit that supports Diagnostics and transfer it to the Selected Units window. We close the dialog with OK, save the project, activate generation, and then start Runtime. Once a process fault has been triggered for which there is monitoring, a window is opened in which the state fault is announced. We acknowledge the message and switch to Overview. There we can identify the faulty unit and by pressing the F1 button, the faulty subunit. Here the state graph clamping device. We change to Detail View to see the addresses that caused the fault, plus the level, unit, state and transition in which the fault occurred. With the F8 button, we can display the operations with which the addresses that caused the error are linked. If you click F8 again, you get the links displayed in ladder. At this point, we would like to point out that there is a whole series of knowledge elements available on the current topic. The sample applications include extensive documentation, plus a sample code that can be run immediately. With this code, you can simulate different types of faults on a user interface. Using the instructions step by step, you are guided through the configuration of several cases of process diagnostics. The following has been published to date. The applications are available in our Internet shop at the following link.